Hello, my name is Carter. I'm explaining my internal flow and extended Bernoulli problem. In this problem, there's a large pipe, and on this pipe, there's going to be two different pressure drops based off two different volumetric flow rates. In this problem, we know the density and viscosity of the water from table A1, and we also know the diameter, length of pipe, and roughness of the pipe. In this problem, we need to assume that the flow is steady state and incompressible, and that there's no frictional losses at either end of the pipes due to entrance and exit effects. And then next, in order to start solving the problem, we need to find the velocity due to each volumetric flow rate, and that's going to be from the continuity equation. Once we have the velocity, we're going to move to finding the Reynolds number, and the Reynolds number will tell us if it's laminar or turbulent. The first flow is going to be turbulent because the Reynolds number is greater than 4,000, while the second will be laminar. From there, we can determine the frictional factors using the respective equations if it's turbulent or laminar. And then once you have the friction factors, you can use the extended Bernoulli equation and use the friction factor to find the frictional losses and set that equal to the pressure drop. And then from there, we can determine the pressure drop. The pressure drop for the turbulent flow is much larger than the laminar. This is my problem on pumps in MPSH. In this problem, we have a pump that is elevated 5 meters above a tank of water, and the pump is pumping out of the water. We're given an equation for the available MPSH and the MPSH required, and we're given all the parameters for those equations. In this problem, we need to assume a few things. The first, that the flow is steady state and the water is incompressible, and also that the water at the tank and at the pump is open to atmospheric pressure, thus the pressure change is zero. Known as this problem, we know the diameter pipe, the change in the height in the pipe, the shutoff head, and then the density of water, which is from table A1. In order to solve this, we're going to set the MPSH equation equal to the MPSH required equation and then solve for the volumetric flow rate. Once we have the volumetric flow rate, we're going to use continuity to find the fluid velocity. In this problem, we'll be explaining a porous media and extended Bernoulli problem. In this problem, we have a large tank of water above coffee ground tube, and in that tube there, we're going to determine the superficial velocity of the water flowing through that porous media. In this problem, we need to assume that kinetic energy can be ignored because the flow is so slow, it's trickling flow, and then also we need to assume that the water is released to and from atmospheric pressure, therefore pressure change can be ignored, and also that the flow is steady state and incompressible. The knowns in this problem are the density of the water and the viscosity of water from table A1, and also we know the diameter of the tube, the initial height of the fluid above the tube, and then the particle diameter, and then the permeability of the bed. From there, we're going to use Darcy's law because the flow is trickling to determine the superficial velocity. In order to find the superficial velocity, we first must find the frictional losses from the extended Bernoulli equation, and using the extended Bernoulli equation, we can determine the frictional losses from the change in height of the fluid. And once we have the frictional losses, we're going to plug that into the Darcy's equation to find the superficial velocity, which turns out to be 7.589 times 10 to the negative 4 meters per second squared. And then to check if our Darcy's equation approximation is valid, we check the Reynolds number using the superficial velocity, which turns out to be 0.141532, which is very low, which means the Darcy's approximation is valid. In this problem, we're going to be examining the external flow over a golf ball that's dropped into water. We want to determine the terminal velocity of that golf ball in the water. In this problem, the knowns are the density and viscosity of the water, which is from table A1, and we also know the diameter of the ball and the density of the ball. And then we also know the coefficient of drag due to laminar flow over a sphere is 0.5 from handout 11, and the acceleration due to gravity is known. Next, we assume the drag coefficient is constant, and then the mass of the ball is not changing, and the flow is laminar. And in order to solve this problem, we're going to first set up a net force equation, which is going to set the drag force equal to weight minus the buoyancy force. And once we input equations for both the drag force, weight, and buoyancy, we can solve for the terminal velocity. Once we have the terminal velocity shown in this equation, we can use that terminal velocity to check if the flow is in fact laminar. And the Reynolds number turns out to be less than the Reynolds number required to be laminar, thus the terminal velocity approximation is accurate. In this problem, we'll be going over the Navier-Stokes analytical and numerical solving, microscopic mass momentum balances, and boundary conditions. In this problem, there's a distribution block which water flows through it that is fully developed, and we want to find the velocity profile in that block. The flow is pressure driven, and in this we have a few knowns. The first is the density and viscosity of the fluid from table A9. We also know the diameter, height, and length of the distribution block, and we know the pressure before and after the water flow. In this, we need to assume that the fluid is Newtonian, its constant density and viscosity of water, and then we also know the flow is laminar, the flow is pressure-driven, steady state, and we also need to assume the flow is one-dimensional, meaning it's only flowing down the distribution block. To solve this, we set up a microscopic mass and momentum balance. The continuity equation will be reduced based on the assumption of steady state and one-dimensional flow, and from there, you set up a momentum balance, and that momentum balance will yield this equation right here. That's from the assumptions of steady state, the continuity, and one-dimensional flow. And with that equation, we can integrate that twice to get up with a velocity profile. However, that velocity profile will have two constants of integration. To find those constant integration, we need to set up two boundary conditions. The first boundary condition is that there's no flux at the middle, meaning that y equals 0, the change in velocity in the direction of y is 0. This will give us that the first constant of integration is 0. Next, our boundary condition 2 is that there's no slip at the walls, meaning at y equals d divided by 2 plus or minus, the velocity x equals 0. This will give us the second constant of integration, and from there we'll have a velocity profile, which is shown right here, and that is the analytical method. Next, we can do the numerical solving method using finite difference formula. This formula, shown above right here, is for using the central second derivative method, and from there we can come up with an equation for the velocity in the x direction at any node is dependent on the velocity at the node in front and behind it. From there, we insert that equation into Excel, and you let it do iterative calculations to determine the velocity profile. And that velocity profile is then compared to the analytical equation determined. And that created this graph. And therefore, that's going to be your final velocity profile. And actually, the analytical and numerical method from finite differencing is exactly the same. And that's why we can only see one profile, because they're in fact overlapping each other. This problem we be going over compressible throw. In this problem, we have a fighter jet that's flying at two different elevations, and we want to determine the speed of sound at both of those elevations. And in this problem, we have knowns of the temperatures at both elevations, and we also know the R from handout 1, the gas coefficient, and then we also know the specific heat K values at both elevations. In order to do this, we need to assume that the isentropic compressible flow, and also that the specific heat K is constant. To do this, we're going to set up the speed of sound formula, which is speed of sound equals to kr times t to the square root. And we're going to input the values given above, and we're going to see that the speed of sound at the higher elevation is going to be much slower than the speed of sound at the lower elevation. This is due to the height being the density of air is going to be much lower at the higher elevation, meaning the speed of sound is much lower. Thank you.